Okay, welcome back everybody. We're going to start again, and now we're going to hear about a UXor among FUors.
Thank you. My name is Ágnes Kóspál. I'm based at Kóspál Observatory in Budapest, Hungary, where I'm leading a research group with the generous support of the European Research Council. And with my colleagues, we are studying the relationship of the disk structure and the time variable accretion. So I thought at first that my talk would be a little bit of an outlier among the talks or concerning the topic of this conference, but already this morning we heard that there's actually some relationship between the UXor phenomenon and accretion. So today I'm going to talk about a very specific young star, V582 Aur. But to give you a little bit of context, this is an artist's impression of the environment of a typical young star, a typical T-Tauri star, and I really like this image because it illustrates all those possibilities that how a young star can vary. So we have some accretion channels here, and then through those material can fall onto a star at a time variable rate. That causes, of course, a fluctuating brightness. Stars, typical T-Tauri stars, late-type stars, of course, may show flares. There may be dark star spots on them because of the magnetic field, of course. And then as the star rotates, that causes rotational variability, rotational modulation. Of course, we have the line of sight obscuration in a system which is close to edge-on, or if there are some material lifted off from the midplane of the disk. So, of course, there are some stars that vary more than others. Some show really extreme variability, and one of these types, Orionis-type stars, or shortly FUors, are really very extreme. They are young stars with large outbursts. They brighten up by 4 or 5 magnitudes at optical or near-infrared wavelengths. And here you can see some Palomar images of the first few objects that were discovered to exhibit this phenomenon. You can see some reflection nebulae around them, and if you collect broadband photometry and construct their spectral energy distributions, you will see that they all show infrared excess, as young stars should. They have very specific spectral characteristics as well. And they have a spectral type that depends on the wavelength you look at, and you can understand this if you consider that if you look at such a star, then you don't really see the star, you see the accretion disk. And then, of course, that you see a hotter region of the disk at optical and a colder region of the disk at infrared wavelengths. They have some other spectral characteristics like blue-shifted absorption in the Balmer lines, or CO band-head absorption, which are also all related to a circumstellar matter. So here you can see some example light curves of FUors. And now we know that the physical cause of this significant brightening is a powerful accretion outburst due to some kind of instability in the inner disk. Accretion from the disk onto the star becomes much more effective, and then a lot of material is dumped onto the star. It heats up, it brightens up. The accretion rate can go up to 10⁻⁴ solar masses per year. And of course, that means that not only in the B band or in the photographic band they brighten, but they also brighten throughout their SCD, basically not only in the optical, but also in the infrared. And their peak bolometric luminosity may reach several hundreds of solar luminosities. So that's much higher than a typical T-Tauri star, which is only a few solar luminosities. Of course, if you imagine that a boring little young T-Tauri star brightens up to several hundreds of solar luminosities, that may have substantial effects on the disk around it. Such an outburst may induce changes, especially in a terrestrial planet-forming region at a few AU distance from the star, like structural changes, because you can imagine that you evaporate some of the dust grains that may otherwise could have formed planets in the disk. There may be mineralogical changes, like you may change crystal structure of the dust grains. There may be chemical changes, like you evaporate ices, you move the snow line, or you catalyze some chemical reactions that would not happen otherwise. But also, there may be effects that you can also see directly in the light curves. And I would like to highlight here two very interesting events that our Russian colleagues studied and made significant contribution here to this field. These are events in V1515 Cygni and V1055 Cygni, where there was variable extinction due to dust condensation in the disk wind. So I'm not going to talk about these objects, but I'm going to talk about another object that I'm really interested in, V582 Aur, which is a FUor type object. It produced an outburst sometime between 82 and 86. It's located in the Auriga OB1 association at 1.3 kiloparsec in the galactic plane, and it's surrounded by a group of young stars highlighted here by the blue and red symbols. So it's not an isolated young star, it has its siblings, and its outburst luminosity is between 150 and 230 solar luminosities, so it's quite bright. This is what its outburst history looks like. Some Bulgarian colleagues worked on this light curve. So here you can see this time range I mentioned at the beginning, that the outburst was sometime between the 80s, first half of the 80s, let's say. And in the past, let's say, a decade or so, there's been very frequent monitoring of the object, and you can see that it doesn't have like the usual plateau phase or a slowly fading phase like what's typical of FUors, but it varies a lot, several magnitudes actually, in all colors. So these are optical light curve BVRI. So we became very interested in this object, and we decided to do our follow-up, and we did a photometric follow-up using our 1 meter class telescopes in Hungary. We obtained optical BVRI images, photometry, and also at Teide Observatory in the Canary Islands in Spain, infrared images and also optical images. We did some spectroscopic follow-ups as well. We used telescopes in the Canary Islands, Roque de los Muchachos Observatory, the 10-meter GTC telescope, and with the 4-meter William Herschel telescope. These are optical and infrared spectra, and we also took some spectra at the Calar Alto Observatory. So that's the optical infrared part. We did our job also at millimeter wavelengths. We used the IRAM 30-meter single-dish radio telescope at Pico Veleta, Spain, and we used, at that time it was called the IRAM Plateau de Bure interferometer, which is now the NOIMA. This is an array of 50-meter radio antennas, and here we targeted 2 different CO isotopologues and the 3-millimeter continuum. But before I show the results of these new observations, we actually went back to the 70s and 80s, and we checked our Schmidt photographic plate archive to see if we can constrain more when the outburst happened. And we found a couple of glass plates that covered the area around the star, and we found the location of the star. We scanned the photographic plates and found out that at the end of 85, the star was still invisible, while at the beginning of 87, it was already in outburst. So we could constrain the eruption happened probably sometime in 86. Concerning the optical and infrared environment of the star, here we can see a color composite using JHK images, so near infrared, and you can see, of course, the star or the central bright source surrounded by a little bit of faint nebulosity. And this is really interesting because this is bluer than the source, as you can see in this color composite. But it is also very interesting because as I will show you later that during our monitoring, the central source changed its brightness, but we made a photometry on these pixels as well that cover this nebula, and the nebula was constant throughout our monitoring. So that already gave us an indication that the brightness changes towards the star may be because of some kind of changes in the line of sight that did not affect the illumination of the nebula. This is a scattered light nebula. And also this nebula was not seen before the outburst. Concerning its millimeter environment, here you can see these maps show with the color scale the integrated CO intensity map, 13CO, C18O, and with the contours the continuum map, and here is the line profile if you integrate everything throughout the map, and this is just a central beam. So you can see here 2 velocity components, but only one actually belongs to our target. And there's also a continuum source there, and then also a CO blob. So we can measure the flux, continuum flux or CO flux there, and convert that to circumstellar mass, total mass, and we get something like 0.05 solar mass. So this was a work done by my PhD student, Fehér, who later went to work as a postdoc at IRAM. We also wanted to say something about the progenitor of this object. We collected pre-outburst observations, which are plotted here with the open circles. And then, what you don't really see, but I can point out that the next step was that we took the Taurus median, a typical SED of a typical T-Tauri star in a Taurus star-forming region. We reddened it a little bit, and we scaled it to 1.3 kiloparsec. And this is what it looks like. So the first part, actually the optical part, overlaps very well with the observed data points. So this suggests that pre-outburst, this object was just a regular T-Tauri star, and then the circumstellar mass that we measured for it also suggests that it's a normal T-Tauri, late-type T-Tauri. And later, of course, during the outburst, it brightened at all wavelengths from the optical to 100 micron. And then, of course, when later it showed the variability, then again, that has a different color. This is what our light curves look like. You can see here again the optical part, BVRI, and then some near-infrared, JHK, and these purple dots are the 3.6, 4.5 micron Spitzer and Weiss observations. So what you can see here also, I marked with these dashed vertical lines are optical spectroscopic observations, and the dotted vertical lines are the epochs of our infrared spectra. So you can see here 2 very interesting events, one that happened at 2012, and another one that happened in 2016-17. So these 2 fading events. And of course, we timed some of our spectroscopic observations to measure the object in the minimum and some in the maximum to see what happened between the 2. So for our optical spectroscopy, the first 2 spectra were taken during minimum, and then one during the rebrightening, and the last one at maximum. And there's actually not much change between those. And then as a comparison, I copied here the spectrum of FUors, the prototype FUor, and then the G0 type, supergiant type stellar photosphere, which is also very, very similar to what we see here. So what you can see here is some metallic absorption lines. H-alpha metals don't really change that much. H-alpha is a little bit variable, mostly the emission component. The absorption component is less so. So what we think is that maybe accretion fluctuated a little bit. The wind was probably constant throughout our monitoring. The infrared spectroscopy, this is what our infrared spectra look like, and this was the highest one was taken before the 2012 minimum, so this is a maximum spectrum, and then these were taken, the color curves were taken during the 2017 minimum. And what you can see here again, not much change in the shape, but if we try, we try to correct the color curves for 7 magnitude of extinction, and that's shown here with this gray stripe. And then with that correction, you can basically reproduce the maximum spectrum. So the change between 2017 and 2011 was, again, just changing AV. You can see the typical CO absorption, broad water vapor bands, some faint hydrogen lines. These are all typical for FUors. Of course, we were interested in to do something quantitatively also with our photometric observations. So the 2012 minimum was not really well sampled in the infrared. So this is a J-H, H-K. color diagram, but we measured a lot during 2016-17. And here you can see how the object moved. So it's more or less parallel with the reddening curve. So this also suggests that this minimum was due to changing extinction. This is another representation of the same data. These are color magnitude diagrams, so V versus B minus V or V minus R or R minus I. And this is a comparison UXor ionings, because of course at that time now we realize that something similar happens that what's happening in UXors. And indeed what happens here is that when the object is brighter than about V equals 16, then it moves along the reddening path. But then if it fades even fainter, then it deviates from its trend and it becomes bluer. And this is this famous bluing effect that we already heard about that happens in UXors. And this may actually also work in our target. Basically, you imagine a dust clump that obscures the star, but it doesn't obscure the area from where the stellar light is scattered. So it becomes bluer because of that. To quantify this even more, we applied a Sakura-Sunyaev accretion disk model to our observations. It's an optically thick, geometrically thin, steady accretion disk model, where as a function of our radial distance from the star, you can calculate the temperature this way, and then from the temperature with the black body, the emission of each little ring along this disk, and then you sum that up, and then you can calculate the acidity of your object. And we fixed a couple of parameters, and then the two parameters that we changed during our modeling is the AV, the extinction, and the m dot, the accretion rate. And then we fitted an accretion disk model, changing these two parameters to each epoch where we had multi-filter observations. And this way we could construct an accretion rate curve and an AV curve as a function of time for our object. And for comparison, this is just a repeat of the I-band light curve. And what we found is that the accretion rate was more or less constant between 2012 and 2017, while the extinction increased during the two fading events that we studied, from about 4.5 magnitude to about 12.5 magnitude. And this is, again, the difference between these two is the same 7 magnitude that I mentioned when I showed you the infrared spectra. And these are just a slide about our latest results. So we, of course, didn't stop with the monitoring in 2018, but we obtained a few more data points, and we also added a data point from 1998 when Tumas observed this object, and we fitted those points as well, and now we have a much longer curve for the accretion rate and the AV. And what you can see here is that now we can discern a slow fading or slow decrease in the accretion rate. That is probably what you would expect for a FUor that has been in outburst since decades. Now we can see that it's going slowly back to quiescence, while the extinction was pretty much the same in 98 and 2018. So now we can measure already a factor of 2 decrease in the accretion rate, and this work was done by my PhD student Gabriela Zsidi, who is working at ESO right now. You can also see this in a color magnitude diagram where the latest points, basically everything since 2014, align with the extinction path, but it's shifted downwards along the v-axis compared to observations before 2014. So this is this general fading trend because of the decreasing accretion, and superposed on that, there's the accretion, the extinction changes, the UXor phenomenon, basically. So as a summary, we have our target, V582 Aur, which is a FUor. We could constrain it, that its outburst happened in 1986. Its progenitor was a regular T-Tauri star. It showed 2 deep dimming events caused by increased extinction. That's a little bit like the UXor or Dipper phenomenon. And then we can also start thinking about what the origin of this extinction can be. So, because there are two of them, one in 2012, 2016, 17, we can assume that it's periodic. And then, of course, you can calculate all kinds of parameters for an orbiting dust cloud that may cause this. But, of course, the shape of these minima are not quite the same. So it may be that it's not a single dust cloud that's orbiting, but something that comes in and that it's being destroyed, and then something else again comes in, and then it's again being destroyed, like these kind of infalling giant comets that sometimes are invoked. So that's still not clear. We continue this, and then let's see what we'll find out in the future. Thank you very much.
According to a classical model of FUors by Ágnes and Kenyon, a FUor is not a star but self-luminous accretion disk. And what is radiated in optical region is a disk of size about 1 astronomical unit. So you have to obscure not the central star but the whole disk of this size.
Yes, that's true enough. Yes, that's what's happening. I don't know. You need something big. You need something big. So actually, from the time scale of, if I can I move back? No, I can't move back. In any case, so we from the time scale of these minima, we try to basically figure out how far it should be and how large this obscuring thing should be along its orbit, and we got several AU. So with that size, you can really obscure part of this accretion disk, hopefully. I really need this.
You're right about the classical model. You worry the inner viscous disk and MRI of thermal instability, but there are other mechanisms for triggering. And one of these is a clump rotation. Fragmenting disk produce clumps which migrate inward and disintegrate about at distances where Ágnes now placing the shape about several astronomical units. So it might be a trace of disintegrated dusty, gaseous and dusty clumps that has releases portions of the atmosphere and produces clumps and structures.
Exactly, yeah. Thank you for the comment.
When you calculate your model, disk and so, what was inclination adopted?
Do you remember, Peter?
Inclination.
Inclination.
To the line of sight.
Since we don't know, we just assume
40, yeah.
Okay, I mean, it's very interesting about geometry of reflection nebula. You observed, you told that it has constant
Yes.
brightness, and during the fading as well?
Yes.
And so it's very interesting how it could be in this case. And you did not mention possibility to obscure the central source by dusty wind.
Yes, that's also possible. So we see wind signatures.
Argument
Yes.
or no?
Well, we see wind signatures in H alpha, but not really in other lines. Well, we don't really have very good signal-to-noise spectra, so there's definitely room for improvement there to study what's happening with the wind in time as well.
Sorry, you showed light curves. No.
Yeah.
Of some old.
This,
This one, and you see plateau V10, 57.
Yes.
You see the plateau, and it is assumed that it was due to dust obscuring of the region. Yeah?
Yes.
This one.
Yes.
So
Yes.
why not in?
Yeah, why not? Yeah, here something analogous may happen. Exactly.
What is the reason of shift on the color magnitude diagram in the upper part of this diagram?
So the shift maybe, I think, is because there are two effects that happen at the same time. And one effect is that the accretion rate is slowly changing, so the whole acidity in all colors are just self-similarly in a gray way decreasing. And on top of that, there's also a color-dependent variability that is the reddening that is caused by the obscuration events. So these two effects are superimposed to each other.
An impression is that this shift in vertical direction can be explained by the presence of large particles with local extinction.
That's also possible, yeah. Basically, I think just with photometry, there's no way to distinguish between slowly changing accretion and adding gray dust to the system. So somehow, in some other way, we would have to somehow distinguish that. I don't know how.
Okay.
Thank you.